So now let me reiterate what we talk about. First of all the videos are up, including yesterday, quick session on how do we design a GPU and kind of like an intro to GPU. And the assignment 4 is now extended to July 14th. If you are done already, please submit, because I mean it's auto graded anyway. So if you submit by the original deadline, the usual, you get 10% extra credit. By this point, you can break up extra credit to the point that you can probably get 50% on an exam and you still get an A. If the task 1, task B, test, and DLC, yes, then you're good, you're done. In class due today, can you give answer sheet after today? Yes, for sure. And I feel like would it be good if I extend it in class to maybe next class, like next Tuesday? Because I feel like you guys are still like going through A4 and still trying to process everything. Okay, let me do that right. Remind me at the end of the class to do that. But it will be extended to Tuesday. What else? Oh, okay. So there was a question that can you use a constant 0x f f f f f f f f in your assignment, right? So you can use a constant up to 0x f f and that's all. Otherwise, the DLC would yell at you saying, "Hey, the constant is too big." But that's a good trick on how to get 0x f f f. And what if we do about shifting to the right with sign extended? So let's say I want 0x f f f, right? One thing I can do is to do 1 left shift to 31 and then right shift again to 31. What would that do to my number? I shift 1 all the way to the leftmost bit, and then I shift it all the way to the rightmost bit. Now I got a sign extended. Yes, -1. Thank you. All right, so there's a good trick, 2 operations, and now you get -1. So if you want to use 0x f f f f f f f, just remember that you need to, right now, the trick is going to spend you 2 operations for that. What do you need 0x f f f f for? I'm just curious, actually. It's more like now it's my curiosity because I don't think any of the questions need that. Two to the 31 given. Well, it is a sign number, right? So 2 to the, yeah. If you think about it, once you extend the number 1, it's overflow, right? Basically, you left shift to the point that it overflow. That's why it becomes a sign number. Oh, okay, yeah, sure. Uh, exactly, yes. So for task 2, the 3-bit variance, if it somehow RSP got in, that becomes the 4-bit variant. Yes, you got it correctly. Seems like you're almost done. Task 2 is actually really easy. To be honest, if you haven't started task 2 yet and you're like stuck with task 1, go to task 2. It's actually really, really easy. Task 2 is a really big giant if else. It's actually just a giant if else statement. And I mean, all right, who have done task 2 or who are working on task 2, do you think it's easy? At least it just grunt work, no thinking. Yeah, it's much easier. It's actually really, really, really easy. So if you are stuck on task 1, switch to task 2. That's almost like a free point for you guys. Yeah, just print the heck out of it. Yes, exactly. It's a bunch of evals. If you understand how the translation between assembly into binary work, and then the rest are simple. You see bits coming in. You check the bits in the evals, and you print the heck out of whatever you saw. It's actually really, really easy. All right. Yes. Yes. So task two, so to put into some more context, right? What you're gonna see in task two, it's like a freshman class at Carnegie Mellon, but what you saw in task one is like a first semester sophomore kind of assignment. Or to be honest, it's like either second semester first year or first semester second year. But task two is the easier. Usually that assignment will be on the easier class. So you can probably guess task two is going to be easier. Yes, the five variants and the register can be different. The input, yes, when I grade them, they can be different. I can just copy the main function into your file and run it if I want to. I can also use scripting. Maybe I should. There was a time when I was like, you guys can put the test code on GitHub and I'll pull everything and I'll test everyone else. But I don't do that anymore. Maybe I should resurrect that with some scripting because that was a pain to like include everything. For the future semester, not your semester, not this semester for sure. Hannah said no main in task two. There's a main there. You can keep it. It's fine. Uh, if there's no main, I'll append. Basically, I'll just quickly check and see whether I just paste my own main function or append the existing main function. Having the main function, to be honest, help me because sometimes the assumption with your input tell me if you have some weirdly like a weird method to process the bit stream. So if you have a main function and you test your code, keep it there. It's actually much easier for me to figure out what's going on. All right, any other questions? Because otherwise I'm gonna go and continue on our Tuesday, not Wednesday, Tuesday lecture. How was yesterday lecture so far? For those of you who are here, any any feedback? Because it feels like, to be honest, I think it covered things that are a little bit too advanced for what you've learned. How computing address work. Interesting. Okay, yes, thank you. Um, that's a really vague word, by the way. But it's generally a positive thing. How computing address? What do you mean by computing address? Wait, what do you mean? Like you don't get the point of like the you mean the LEAQ instruction? Ah, because sometimes like when you write code in C, sometimes you just want to get star P, right? And when you use star P, there can be pointer arithmetic where you just do P plus one, right? Something like P plus one, P plus two, which means that you move the pointer. It's not you change the data or anything, right? But one thing you can do in assembly is then you compute the address and you use the addressing mode so that you do P becomes the base, and then you do the offset of 1 or 2 or 3, right? It's the register, not the memory. So that you can use that register value later as the pointer. So that register becomes a pointer, right? If you think about it, because it stores the address now. It doesn't store a value. Right? So that's why sometimes we need to just say, I want to compute the address because, oh, sorry, if that's more confusing. I see question mark and then now I panic. So what's the in class 9 it's gonna due next Tuesday. Yeah, the resulting number that goes into the register is not an actual data, but now it is an address. So now the register store the address where you can use that register values later as a pointer. Yeah, so basically that's all. The reason why these actually get used quite often, if you look at real code, is sometimes you don't have enough register to store everything, so you need to basically put that in a memory, right? So it can be handy to have an instruction that allow me to compute what's the address, right? That's mostly the reasoning. And then the x86 style of computing the address gives some room to basically do shortcut on the address. Like a plus 10, I can use offset of 10 and then base of a. So with one instruction, I get a plus 10 without actually having to do the add, right? Each register, yes, each register can hold at most 8 bytes in x86. Yep, it's enough for one pointer. Yes, exactly. Yeah. So you can now see that things that you learn kind of fall into places. The way the size of the address would fit the register so that you can use that register to point to the area in the memory wherever you want to point to, right? So things that are being designed in x86 are designed is there for a reason. Uh, like it's 64-bit machine, so an address is 8 bytes, so that's why register can hold up to 8 bytes, right? All right, so let's continue on. Any other questions? Because otherwise, let's continue by going through a basic recap, right? The first recap I want to talk about is please remember the cache organization. A cache contains multiple cache blocks. The cache block can have any size you want, but if you buy a CPU right now, those cache blocks are 36 bytes. It just is configured to be that size because it kind of makes sense for the data or the program that you're using. The size are actually tuned to save the cost and also provide bandwidth and also provide um, like the benefit of hopefully you can take advantage of the way you write the program. And each cache blocks belong to a cache set where the memory address is mapped to a certain set. And here's the organization. If you don't want to memorize this diagram, think of it this way. The cache is a movie theater. Each row in the movie theater is your set, and the seats are the cache block, right? Where you have to go and use the ID, the tag, the number of seats on your ticket to check whether that's your seat or not, right? We talk about set associativity, which basically dictates how many cache block is in a set, right? So a cache block is one single unit. A set contains multiple blocks. If you talk about, say, four-way set associative cache, it means I can hold 4 blocks per set. It's not a mathematical set anymore. I have the maximum limit of how many block per set do I have, right? Uh, and then now I want to talk about cache insertion and eviction. But before that, I want to talk about the benefit of having a larger cache block, larger than a word, right? You might be wondering why you have a 64-byte block. So how many people write code that looks like this? For I equals 0, I is less than, I don't know, 1000, I plus plus, and say you have A of I, you just increment everything. How many people use a loop and go through elements in the array similarly in this fashion? How's your bubble sort? Does it kind of also go this way? Like you have a loop that goes through the index in your array one by one by one. Right? Is this a common pattern in your code? It's a really common pattern, right? So there are two things that you will notice here. First of all, if you look at this array A, right? This is A0, A1, A2, blah, 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 A of 1000, right? What you see is the way you access. If you access A0, what's the next element you're accessing? What's the next element? A1, right? So then you go to A1, A2, A3, A4. This is called spatial locality. What does spatial mean? What does spatial mean? Space, right? It basically means space. Spatial locality means that if I access something, I'm gonna, if there's a likelihood that I'm access something nearby. If I access something, there's a likelihood that I access something nearby, right? And we do that a lot when you write programs, because when we access one element of an array, what's the likelihood that you are going to access the thing next to it? A lot. It's a high chance that this happen, right? So how big is the size of A0? Let's say A is an integer. How big is that? 4 bytes, right? So when I access A0, do I bring in the entire cache block into my cache? Well, it is, right? So when I access A0, I'm going to bring the entire 64 bytes into the cache. So what can I tell about A1, access to A1, A2, A3, A4, A5, A6, A7, A8, A9, A10, A11, A12, 13, 14, and 15? A0 is a miss. Like that's the first time I see that data, so it's a miss. I bring that whole block into the cache. But what can I tell about the access to A1 through until A15? Is that data in the cache or in the memory? Actually, A1 to A15 in this case would be in the cache. Why is that the case? Because A0 is 4 bytes, right? When I access that data, it brings the entire cache block. I bring the entire cache block. And let's assume that's the beginning of my cache block, basically, because otherwise, yeah, I can access another cache block as well. But let's say A0 brings in the entire cache block, and this is my cache block, right? From A0 to A15, because it's 64-byte cache block. I have access to A0. I'm going to bring in A1, A2, A3, A4, A5, A6, A7 with me. They're my friends inside the same cache block, right? Things inside the cache block is like your group of friends. Wherever you go, they go with you. So if I can find you, I then can likely I can find your friends too, right? Um, yeah, sure. So when I have the access pattern like this, right, and I want to access A0, A0 is only 4 bytes, but the way the cache is designed, because the cache block is 64 bytes, when I access A0, I bring in the entire 64 bytes around me into the cache, right? Which means that in the next iteration of my loop, right, I access A0, then followed by A1, A2, A3, A4. A0 is a cache miss. I never seen that data. That's the first time I access the data. So I go to the cache. But when I want to access A1, where is A1? Is A1 in the cache or is A1 in the main memory? Sorry, it was a question, private message to do a recap of this slides. It's gonna be in the cache. So from A0 to A15, how many cache miss am I seeing? One miss, 15 hits, right? One miss, 15 hits. That's a pretty good hit rate. Hit rate means how many times am I seeing a cache hits over the number of cache accesses that I try to check, right? And this is because you have spatial locality in your program. Because you program it this way, you go and increase I, the index that you want to use to access your array, right? What about the other variable What about the variable I here? How many times am I using the variable I? How many times am I doing something with the variable I? Quite a lot, actually. It's actually more than 1,000 because you need to increment that as well, right? So that's comparing, incrementing, and I is likely to be a part of the move instruction because it's AI, right? This, we call it temporal. What does temporal mean? Temporal locality. Is time, right? Temporal means time. So basically what it means is that if I access something, there's a chance I'm gonna access the same thing again in the future. So cache take advantage of both spatial locality and temporal locality to get more cache hits, right? So that's how. But the thing is, cache is limited in size, right? Again, also, cache is limited in size. So we have to think about, okay, how do we insert things into the cache, and what should I kick out when I look at the cache and when the cache is full? That's called inserting is called a cache insertion. Kicking things out is called cache eviction. So let's go through them, right? The thing is, for a direct map cache, how do we insert? What's a direct map cache? How is this? What's a direct map cache? It's something we learned on Tuesday. I know it's 2 weeks before this. One cache block per set, thank you. Uh, Usually by this time, if it's me, right? If I'm in your shoe, I forgot everything. I need to go and review. There's so many things you learn in a week. Direct map cache is one cache block per set. So if it's a direct map cache, how do I replace? What do I kick? If I come in, the cache is that set is full. What's my choice? How many choice do I have for what to kick? What to kick out? Is the only block, right? You only have one choice. You kick whatever is there out and you replace that. So it's simple. I kick that thing out and I replace that empty room in myself, right? So that's a simple part. How about set associative cache? I go into that set. Now I have a choice, right? Let's say it's a four-way set associative cache. How many different blocks can I click? It's a four-way cache, so I have how many choices? 4, right? I now have a choice. So what are the issues here? How many of you think that some blocks deserve to be kicked more than some other blocks? How many of you think that's true? In order for, let's say, the goal for me is to get the most cache hit rate, would it be making sense that maybe some blocks that is definitely have to be some rules, right? Because how many people think that certain cache block might have lower reuse than other? I don't like I bring that thing, I access this one, I never use it again. But there might be also some data that I access them pretty often, right? Is that true when you write a program? Some array get accessed more often than other arrays. Is that the case? Yes, right? Some array is going to get accessed a lot. It's used in the innermost loop. Some other array, you use it once and then you're done. And then you process certain thing and then you need to use it again, but way later, right? Which means that not every single cache block is equal. So here comes our key issues. The obvious issue is who to kick. Eviction? How do we pick what to kick, right? Then there's also two more issues about insertion. If I am the new guy into this set, where am I relative to the other cache block, right? That's insertion. What's my priority? Should I be kicked out as soon as possible right away if I don't have anything, any reuse, or should I prioritize myself, right? Then there's the promotion. If I have access, if I have a cache hit, what does that tell me about the block that have a cache hit, right? So that basically the issue about kicking and the issue about if I'm the new guy, who am I compared to everyone else in a set, right? Are we all here? Are we all on the same page here? Because we have a choice. Just because we have a choice, right? Are we all in agreement here that we have to make the choice? There has to be some rule. So let's go with that assumption. We do have a choice. We are human that can make choices. Computer, we because we design computer, we can design so that they can make choices. Let's look at the first thing, cache replacement policy. Cache replacement policy dictates when my set is full, how should I kick things out? What to be replaced? Right, this is called the cache replacement policy. So what are some of the possible policy? Can someone come up with some policy here? It doesn't have to be. So I will tell you one thing. In reality, nowadays, that's a good policy, but there's no perfect policy. So last use is actually a really good policy, right? Least access. So why is least access good? Do you want to kick the least access or do you want to keep the least access? So as you can see, there are multiple policies, and actually these are all good options. You can randomly pick. You can randomly pick. You can kick the oldest one first. You can kick the oldest one first. You can look at last use, right? Random sounds risky. Actually, true and false at the same time, depending on the condition. But there's actually one policy here, right? That not last use, but inverse of that. What is least recently used? Is it's not the oldest in a sense that's not the oldest to be inserted into the cache, right? But it's the oldest guy that no one accessed ever, right? No one cares about that block, so maybe I can kick them out. And to be honest, your CPU, the cache in your CPU, the cache even in your GPU, will try to have a policy that reflects these least recently used. That's why I love your answer, because when you mention last use, I think you want to keep the latest one that you use, right? And you want to kick the least recently used, which is actually the policy that most modern processors go for. Why does that make sense? Why does that make a lot of sense to kick the least recently used? I'm gonna wait one minute for you to kind of type the explanation. This is a design thing, right? So we can make a logical reasoning on which one is better, which one is worse. Exactly. Oh, I love that answer. It's least likely to be used in the future. It's least likely to be used in the future. That is great. I love that answer because once you come up with that solution, actually, this is a really, really important solution, right? There's actually a paper, like a research paper that are really important for cache design that say if you can predict the future, you want to kick the one that's used the furthest in the future, which kind of go with the least recently used, right? Because that's kind of like a link between the two policy. So let's look into least recently used. These are based on both temporal and spatial locality, right? If your block has a good temporal locality, they're going to be used again. They will have some reuse. So they're not going to be in the least recently used block. If they have spatial locality, again, they're going to be reused in the block, right? So they're not going to be the least recently used one as well. So if you go with this policy, it's likely that you're doing a good job managing the cache, right? So the benefit is likely to be effective. Yay, right? So you guys are getting the policy that actually is really effective and used in the real world CPU. Awesome. How to implement LRU? This is called LRU. How to implement this in hardware is really hard. So the manufacturer actually imitate the least recently used. It's not a perfect LRU, but it's close enough, but it's much cheaper. Ideally, you want to have this. So what's the downside? Comparison, like sorting. Basically, LRU requires some sorting. Sorting in hardware is not easy, right? Imagine you have to build a hardware to do sorting. It's actually annoying. Um, and as you have more ways, like 8 ways, 16 way, or 32 ways, get really, really annoying to like sort every single thing in there. Why is that the case? Having first in, first out queue in hardware is complicated. Yay. Right? So that's a reality. But again, we would design a policy to reflect LRU, to try to imitate LRU. So we'll go with that. Let's assume every single cache use LRU. Because it's really, really close. The design we have right now is really close to the LRU policy. All right, are we all good here? This is what your CPU, you can assume this is basically the policy the CPU is using. All right. Okay, you guys are done with the cache design. And I'm not joking, actually. This is one of the most important thing in cache design. What's the policy? But let's look at some downside, some weird cases that can happen to LRU. The problem is called set thrashing. What does the word thrashing suggest? What does the word thrashing suggest you? What does the action? What's the action here that happened to your cache set? You throw away a lot of things in there. It's like chaotic, right? You throw a lot of things in there. So the cache block get thrown out. Why? Well, what would happen if you have an application that use a lot of data, but they happen to go to the same set? Imagine this. You have four-way cache. The code goes through access A, then B, then C, then D, then E. I access A, B, C, D, E. And then go back to A, B, C, D, E, A, B, C, D, E, A, B, C, D, E. A, B, C, D, E are different cache blocks in the same set. These are different cache blocks, but all mapped to the same set. I use LRU, and it's going to become ineffective. It's going to become useless. It's worse than random policy. Why? So let's look at this. I access A is in a set. I access B, B is get put in a set. I access C, C get put in a set. I access D, D get put in a set. What happened when I access E? Which one get kicked out? Which of this get kicked out? If I use LRU, am I kicking out A or B or C or D? Which one is the least recently used? A, yes. I will kick A out. I will replace A with E. Now I have access to A. Is that a hit or a miss? It's a miss. And what do I kick out? B, yes. So I replace B with A. Then the next access is to B. So what happened here? So let me ask this question. Will I ever get a cache hit? Will I ever get a cache hit? No, right? Suddenly, from my access from A to B to C to D and back to A, in this loop, I have 100% cache hit. But I have A to B to C to D, then to E in a loop. I have 0% cache hit. See how crazy this can become, right? When you write a program, back in the day when the compiler is not complicated and when the hardware design is not complicated, this thing can happen. This thing can happen and it can actually impact the cache performance. In modern day computing, it's still quite a real thing that can happen, but this gets prevented by a lot of hardware techniques and also compiler techniques um, to prevent this problem from happening. But I want to still highlight that, well, if you have a loop that go into a bunch of cache blocks, this can happen, right? So cache friendliness is an important topic for high performance computing. You want to write a program that run really, really fast, right? And there's still a lot of application that demands fast code, right? For example, this is one of the example that I was actually, to be honest, personally surprised as well that it make this much of an impact to write a really fast program, right? How many people know DNA sequencing? A little bit, right? So what can they use for? So I guess what is the benefit of be able to know your genetic information? Well, obviously know who's the father. I guess who could have been your parents, right? Um, you can also check out whether you're gonna be having certain disease, right? Because these are some disease are tied to genetic information, right? It's related. And I should be, to be honest, I kind of got lucky because I had a chance to like chat with my wife a lot, and she is a medical doctor and do a PhD in uh like genetics, and she kind of told me how important it is to be able to quickly sequence the DNA. Why is that? So let's say you're looking at a patient, like let's say some newborn baby that got born with a genetic disease. How many of you think that if I don't treat the baby, he or she might die within a few days because of the genetic disease? And I have no idea what are the possible disease, right? Is that an important problem? The thing is, the current technology, right, even at the top medical school, it's actually pretty hard to do this quickly. It's pretty costly as well, right? So it's surprising quite a lot that, hey, if I can accelerate, make DNA sequencing maybe 3 or 4x faster from 4 days, what if I can do it in 18 hours? I have the sample in the morning, the doctor go and with his or her day, right? Go and treat the patients, come back to the lab results in the evening, and now you see the result of the sequence of the DNA sequencing you just launched in the morning. You're likely will save a lot of life, right? Compared to when you can do it in 4 days. Because by that time, there might be a lot of patients who suffer from the disease, and if they're just newborn infant, they can die. Then they will likely die, right? So you can now imagine that writing fast program, like caching, actually, these things that you learn are actually really, really important to DNA sequencing because you want to make sure everything hit in the cache as much as possible, right? These are one of the things you can do to accelerate your program. But there are more. There are more. Basically, try to utilize the memory better, try to use the GPU, try to come up with the new hardware. All of these combined, we can kind of basically advance the science capability, I guess, so that we can do awesome things and save life, right? And this is actually something that surprised me because like I back in the day, I just make jokes that what I do is just make computer faster. Right? I build hardware and just make computer faster. I never imagined the result of that. And now that I get older, I guess like, yeah, there's quite a lot of benefit in that. I can now use the computer to do complex climate simulation, right? To figure out, are we gonna all die because of climate change? Which we might be, right? We might as well be if we're going at this rate, right? So these are all important questions, right? All right. So now that I kind of go really sidetracked from set trashing, as you can see here, writing certain programs, if you're not being careful, it will miss all in the cache. It will all miss in the cache. Sorry about the sentence structure, right? So your program can suddenly get a lot slower. How about the cache insertion policy? So when I have a cache miss, I bring the new data from DRAM, right? How many of you have a case where you're like hanging out in a group of friends and then suddenly there's a new guy in your group? And then you basically have to kind of like figure out where the new guy stands relative to the rest of the group. Does it ever happen to you and your group of friends? Like when you move school, for example, like from your high school to here, right? Okay, God. Have some friends, folks. If you don't have friends, I'm sure you're making jokes. All right, you two make friends. Um, yeah, if you, oh God, but you're all on campus, right? So go and hang out and start having group of friends. COVID is really bad again, to be honest. So be careful, folks. It's actually spiking up again. Um, yeah. I was about to say that, hey, go make friends and hang out, but just be careful to don't get COVID. Um, but the insertion policy is kind of like that, right? I have a group of cache blocks, and I brought in a new block. The new block have to kind of figure out where he stands among every other block in the group, right? So the policy matter. Uh, DRAM typically the way it's treated is if I have a cache miss, the new guy with the most recently used. Why? Well, I just accessed that, so it should be the most recently used. Why are these important? Does it make sense to be the most recently used for most access? Most new block, I would just say, hey, that's the most recently used. Does it make sense to you? Does it make sense for you guys when I say, hey, I just mark it as the most recently used? Yes, right? I agree. I totally agree. I totally agree. Except for a few edge cases, a few corner cases. For example, how many of you write a code that just do something like this? Something like I'm gonna init that number to 0, and I just multiply everything by 64 to make sure it jumps like from cache block to cache block to cache block. How many of you write codes like this? Well, assuming that you initialize some number, but then you skip to another cache block and do the, well, assuming that you have that and no seg fault, right? This can happen. I just initialize everything to 0, right? Do I have any reuse? Do I have any reuse? Sure. All right, sorry. How about a linked list? How about a linked list? All right, scrap this example. How about init a linked list? I just create a linked list, initialize everything to 0. It can happen, right? Do I have reuse? No. So most of the time, most of the time, most recently used makes sense, and it should be used for most of the time. But in the hardware, What if we can detect that that block get read once and never again? They exist. This kind of access also exists. So from the hardware point of view, right, you can always assume that everything will be most recently used, but also be aware that the cache in the hardware actually can be smarter than this and try to detect when you have initialization phase and you touch the block once and never use it again, it try to make sure that that thing get evicted and not wasting the space in the cache. Promotion is simple, actually. Is whenever you have an access to the same block, right? When a cache block is accessed again, it's a cache hit. So what's the policy that makes the most sense? If I use LRU, is that going to become the most recently used? Does that make sense? All right, maybe you're tired. This makes sense. The answer is it makes sense. If I have an access to something, that thing becomes MIU, most recently used, right? And this can be done in hardware quickly by just flipping some bits. So these are actually a simple policy. All right, so we are done with eviction, insertion, and promotion. What else? There's multiple type of cache misses as well. If you look at the classes of different cache misses, compulsory. What does the word compulsory mean? What does the word compulsory mean? Is you have to do it. You have to happen, right? Basically, this is the first time I see the address. They're gonna be a cache miss, except you do a fancy trick called prefetching. We are not gonna talk about prefetching. I put it in here just to make sure that hey, it's not always bad. But when you look at the address for the first time, it's gonna be a cache miss unless you do fancy trick with it, which we are not gonna cover. Conflict miss. What does conflict mean? What does conflict mean? It means that there's some argument, there's some problem, right? The problem is because I have data mapping to the same set. I have data mapping to the same set, even though I have still room in other set. I have conflicts because that set is full. That set is full. All right. Capacity miss, as the name suggests, my whole, like the total, everything in the cache is now full. The cache is just too small to cache everything, right? How can a conflict happen? So you can write a program, for example, where you loop, right? You loop. But somehow when you loop, the address that you access has the same index bit. That's it, right? You're not filling in any other set at all. You go to set 0, for example, or you go to set number 4, or you go to set number 6, right? And you don't do anything with this kind of program. They're just gonna flood a certain number of sets. So conflict can happen. Does hardware do something to solve conflict miss? Yes, there are also tricks in there, but for now, for the purpose of everyone in this class, because you're not gonna go and modify hardware, you can assume the way the set works is you just go and look at the index bit. So it's not deadlocking actually, just go and kick someone else's data out. And that's it. It's not gonna create deadlock. It's just making everything slower. Basically, you're gonna have more cache misses because you kick someone else's data out, right? So your program would turn slower, right? So cache, again, to wrap it up, right? Cache is there to make your program faster, and that's the only purpose. It's not trying to prevent deadlocks or anything. It's just there to make sure your program gets faster. So how do I measure the performance of my cache? Well, hit and miss rate for sure, right? How many times do I incur a cache hit? But you also need to think about the cost of hit and miss, right? How fast is my cache access? What's the total cost of a load? If I have to go and access the data, right? What's the time does it take on average that I need to use in order to access the data? And before we take a quick break, we'll leave you with this example. I have the system with two level of the cache. L1 takes 2 cycles to resolve and figure out whether it's a hit or miss. L2 take 5 cycles to figure out whether it's a hit or miss and also to access the data. DRAM take 25 cycles. And my program, I just write a program, a really quick, simple program with 100 loads. I go to I want to access my data 100 times. And it turns out the hit rate of L1 is 80%. The hit rate of L2 is 80%. How many clock cycle do I have to spend to process all this 100 loads? All right, so we'll do a 10 minutes break. In the meantime, you can take a look at this example. And when we come back, we'll go through this example and talk about how long does it actually take. All right. So I'll be back at 3:17 p.m. Okay, so I'm gonna pause. I'll pause the recorder. Yeah, but don't people get radicalized all the sorry. Just pause this for now with the discussion. Well, why are we still taking a break? Talking about random things. Like everywhere. What I'm talking about is like everywhere, right? You just need to make sure you know what can we believe in, right? It's like when you read a scientific paper and you need to check like what's the fact and see if this makes sense or not. Yeah. I mean, there's also people in Thailand who believe in something that doesn't look sane. Like marijuana is really good at curing a bunch of things, which is insane. And yes, that probably that was insane to be honest. Anyway, so how are we doing with this example? You guys are good at making me going sidetracked. You know that the more we go sidetracked, the less time we have on like hinting for assignment 4, right? Because we're actually almost done with the lecture. But don't we also have crazy people in Congress? A lot of those actually. We have people who believe in GT200. It's crazy. I'm not saying it's good. I'm not saying it's good. I'm just saying that. I'm just saying that they are everywhere, and we should use fact. We should use science and fact. Anyway, so how's our example? Let's go through. Anyone got an answer for this? L1 take 2 cycle, L2 take 5 cycle, and then if I miss an L2, I go to DRAM, and that would take 25 cycle. Let's go through this together. All right. Okay, 400. I think that's the correct answer. So how many of these 100 loads have to go to L2? I have 80% hit rate, right? So 100 go to L1. 20 of them go to L2. I have 80% hit rate, which means that 4 of them go to DRAM. If I have 100 going to L1, that would take 200 cycle because each one of them takes 2 cycle. The other 20 will take 100 cycle. I don't even know why I draw these lines. it doesn't make sense, so I'm gonna erase it. So, and then the other four would spend 25 each, so you get 100, and you add them all up, that's 400 cycle. This might be good, this might be bad. So let's say I think it's bad, and I want to fix it by the same example, load take 2, 5, and 35 cycle. But now I changed the program. I have a really, really, really good L1 hit rate, but I have now 1,000 loads. Is this better or is this worse? Is this a better program or is this a worse program in terms of execution time? To be honest, in terms of execution time, you can't tell, but to handle all these loads based on our assumption, just going to L1 alone, this would take 2,000 cycles, right? So definitely this is worse. I have 99% hit rate. So the other 20 go to L2, that's another 100 cycle. The 80% of those is 4 cycle multiplied by 25, so that's another 100. So in total, you get 22,000 cycle, a lot worse, right? The other example, I have a really terrible hit rate, but I only have a program that has to go to the memory 10 times. This actually might be even better, right? This would take 20 cycles to handle L1. Half of them go to L2, so 5 multiplied by 5, that's 25. Then 40% of that, 40% of 5 is 2 requests going to DRAM. That would take 50 cycles. Am I doing the math right? Yeah. So this is 95 cycle in total, right? So I'm not saying that having better hit rate is bad. Most of the time, having higher hit rate is good. But this example shows that if you try to improve the hit rate, but you ended up sending so many requests to the cache, that can also make the program slower. So in general, right, you want to improve the program performance by, first of all, reduce the hit rate. How? If you loop over a large range of data, trying to make it cache friendly, again, this word. I hope Ajahn Kanat already motivate you by a real example of cache friendly program, but when you make it cache friendly, like when you loop over a smaller size or look at the order, whether I go row first or column first, this can allow you to basically make the program much faster by just changing the loop order. It's actually something really simple, right? You can also reduce the number of memory access. If you don't have to access the data, don't access the data because that takes time. But in most cases, you cannot really prevent that. So what happened with modern library? Anyone use any like modern libraries before? When you use Python and use some built-in library. Anyone use that thing, soup? I think it's called soup, right? The one that process the data formatting. Yeah, JSoup. So are those handy? There's also a library that, yeah, it can be used to scrape website. So that's a JavaScript, I think, right? Rayon, right? How many people use Rayon already on FunPar? You should have, right, by this point. Yeah, it's powerful. It's actually. Do you like it? Do you guys like it? For FunPar folks, do you like Rayon? This is kind of like a parallel. Yeah, it's really easy to use, like cheat codes actually. Um, you name your firstborn son Rayon. It's really really nice too. So there's many libraries that are being used by especially people in the high performance computing community, right? They can look at even things like what's my cache size? So I'm gonna build the program to be cache friendly. or things like Rayon where I can spawn multiple parallel access. So you can build an API that is cache friendly. Standard.io.h is actually not that cache friendly, but if you talk about C++, right? There's a Boost library here. This is another handy library that you can use in C++. It replaced those standard library. So in C++, there's a built-in library for things like a linked list, a map, right? So you can use Boost instead of the default C++ library, and you get much better performance. So this is actually, if you use C++ a lot, I do recommend you to check out Boost. It's a really, really handy library for improving your program performance, right? Uh, so there's also more of these, right? Basically, these are something that some of them actually exploit things like cache hits. Some of them exploit parallelisms. That's why we teach you in fun part that it's really important. So now we're almost done. The rest, right? The last thing I want to talk about is what do I have to do to handle writes? So what does write do to your data in the memory? So what's the difference between a read and a write? Fun part people, what's the difference between a read and a write? Mutation, right? What does mutation mean? You change the content, right? You change the content. Awesome, that's a perfect answer. So when I write to a cache block, the data change, right? So let's say you have this L1 level 2 cache, L1 cache. I use $ for cache. We use this a lot in, it's just acronym. Basically, it's L1 cache, L2 cache, all right? And then DRAM. So let's say I have a write. I forgot to turn on the up here. I write from, let's say I have the value 7 here at address I, right? This is my address. The same address. And then I write to it. I write to I. Instead of 7, I write in number 3. That write is done to L1. But as you can see here, what's the value in DRAM? If I go to address I in DRAM, what number am I going to see there? I see 7, right? Because I haven't propagated that right back to DRAM. So you need to propagate the data to the higher level of the cache so that the L2 has number 3 and then the DRAM has number 3. In general, there are two policies. What is the easier policy is called write through. Write through is every time I have a write, I write it everywhere. Write through is this. Every time I change the number of I from 7 to 3, for example, I change everything to 3. Right? But let me ask you this separate question. What if I modify I from 7 to 3 and 3 to 1, 1 to 0, and 0 to again to 2? Right? I change 3 to 1, 1 to 0, 0 to 2. If I use a write-through cache, do I have to do the same thing for all the levels? And let's say I have the access to I in the future. It's still in L1. Do I really need to change L2 and DRAM in that case? No, right? Because I'll just go to L1 and, oh, that's my data, right? And I will see the new data. So write through is simple. You just change the data everywhere. It's bandwidth intensive because you need to keep changing everywhere. I change 7 to 3, 3 to 1, 1 to 0, 0 to 2. I have to do that for L2 and also in DRAM, right? Another separate policy, because you answered correctly that it doesn't matter as long as I still have I in the L1 cache. If that number change from 7 to 3, 3 to 1, 1 to 0, 0 to 2, and then I read to I want to check what's the value of I will still see the same correct results, even though I don't change whatever is in L2 and L3 and DRAM. So let me ask you one thing. How can I make sure this is still correct? If I is no longer in L1, someone else come in and kick this data out. What do I have to do at the end when I kick the data out? So basically, this is a new scheme, right? Yes, that's it, right? I have L1, L2, and DRAM. And then I keep updating I here, right? From 7 down to 3, down to 1, down to 0, and back to 2. Over here still 7, over here still 7. I mean, I don't care because I still have my L1, the level 1 cache. If I access the data, it's still there, and I get the correct value. I only have to update L2 whenever I get kicked out. This is called write back. Write back is when I kick this block out, I just update this to 2. And if it's no longer in L2, I just update DRAM to 2. That's all, right? Then you don't have to update L2 many times, and you don't have to update DRAM many times. This is what is going on in your CPU cache. This is actually what's going on in your CPU cache. This way, you don't have to update the L2 and DRAM all the time, right? And actually, that's it for the caching lecture. I do have these things that not on the exam. I put it out there. Uh, these are ComArc materials, so I'm not gonna go through them today, but L1, L2, and DRAM hold the same data. Well, it's the same address, so it should, when you want to read that address, you should see the correct data, right? But it's a matter of when do I need to actually update that address in L2, and when do I have to actually update that address in DRAM. The write back, think of it as the lazy update. Like it's lazy evaluation. I do it when I really need to do it. Write through, it's like I'm the active guy. I'm gonna keep writing to L2 and DRAM. So this one thing not over. So is the instruction to access the same data in L2 store in L1. What do you mean? Sorry, I was trying to understand the question. Oh, okay. Yeah, so I want to point out one thing. This is about cache eviction policy, and as I mentioned, there was like a proof that's done a long time ago, right? This is called Bellidy's optimal. Bellady is the name of the researcher. Um, not on the exam, but good to know. Basically, the ideal cache eviction policy. This is a paper from IBM System Journal, 1966. It's one of the high impact paper that kind of prove, not proof, quote unquote, but it has a policy where if you have an ideal insight and you become the person that can read the future, which is impossible, right? But if you can read the future, you want to kick the block that's going to be referenced the furthest by the program. Back in the day, cache, let's call this. So we went along, like we went really far from that time. Like that back in the day, we still don't have the concept of caching, right? Right now it's impossible to implement because you need to know the future, but it's a really good ideal baseline to test the effectiveness of whatever you want to design. Uh, No, it doesn't really use math related probability, but it's more like if I assume that I know what's going to be accessed, you can show that having this policy is the best use of the cache. Will yield the best results if you assume single core machine, like things are done in order. When I say things are done in order, it's like when you have access to A, then B, then C, then D, you issue the access to A, followed by B, followed by C, followed by D. But you need to make sure you know the future, basically. Like, oh, when am I going to access D in the future? If you know that, you kick the things out that's going to be accessed the furthest in the future. All right. So before we leave today, we have in class 10 about caching. You can check it out. This was from an exam from previous semester. It's about how to solve cache related problem. Now I want to switch over to assignment 4. So can I do this on Discord? Do you prefer me handling this on Discord or here? Any preference? In the meantime, while I'm waiting for the answer, I'm going to update the due date for in class 9 on Canvas. Discord chat as well as voice chat. So you can put in the Discord chat. I just need to know where to look because I have only one pair of eyes. So any preference? Oh, then I think you can put the question on the Discord chat. Actually, I would get back to the question being posted. All right, I am modifying the due date for in class to next Tuesdays for in class 9. You have until now Tuesday. All right. And then I'm gonna update the assignment for due date as well. So that you guys have more time to work on it. July 14th, right? So if you still have the late tokens, you can go up to July 15th. All right, everything is updated. Okay, so if you want somewhere to read after the questions being asked, I guess Discord chat works perfectly for you. So let's switch over to Discord. All right, I'll stop the recording right now.